All right, on to the RC circuit. Not gonna lie, the RC and LRC is probably going to take the longest time, just because again, you're gonna have to choose your certain waves. But oh well, let's get into it. So your CSV will have three outputs. You'll have your first column will be your time. Your second column will be your input or your square wave. Your third one will be your output or your RC response. All right, so I graph that here for the full data set. Uh, Basically, you just need to pick your favorite wave. In this case, is the second one. Why did I pick that one? I don't know. This is it truncated. Basically, all I did was just played around with these values until I got it right. I could give you a more scientific answer, but I'm going to be honest with you. It's kind of just what I did. So great. Your lab manual asks you to do the falling edge. I did the rising edge for further analysis. To be quite honest with you, I personally don't care if you do the rising or falling, right? Um, Pick your poison. I specifically didn't choose the falling edge because we see right here we have some nonlinear effects with the square wave. This should be flat. Maybe that's supposed to be a lesson in like, oh, you're supposed to know then to truncate that data, but I, I don't know. You could do the exact same thing with the rising edge. Just be smart about it. So I just use the rising edge. Feel free to follow in my footsteps. So we have here, I just showed you the rising response, specifically the transient section, right? So it does level out up here, does level out before. Um, so make sure you, again, you're going to have to figure out the start of that transience. This one's a little bit easier to find. So here is your input. So that happens at what, 0.114. Looking at this column, this will be your input. So we're about there we go. So we can see here now it jumps up to 1, right? So 1.14. Let's try to make this go a little faster. And by a little faster, I meant a lot slower. Alright, so you can see that it dances around 0 and then just shoots up to 1. So you can basically find whatever that value is. So for here, for me, it was cell 9181. The end of the transients. Once again, this is kind of where you get to deliberate. I just chose 10,001, the fluctuations. You'll see a lot more noise. You can kind of see the noise here. Again, welcome to being a researcher and just have a lot of noise in your equipment, your old equipment. So something to keep a note there. What else can I tell you? Okay, cool. So we have start, end. You guys know if you watch the thermocouple video, you'll have a column for gamma. I'll change this to a number again. So you'll have a column for gamma. Then you'll take the natural log of that column, right? You'll realize, hey, this looks really bad. So what I'm going to need to do is I'm going to have to offset it for whatever that RC circuit was. So the offset for this one will be this time, because again, that's the start. I'm only analyzing this wave right here, right? So that is the start when that step function is applied. I need to know what this value is. So my rise, so in this case V naught, beforehand, it's 0. You can average it out, it's at 0. Um, the plateau peaks out at 1, or should peak out at 1. Some people had a peak to peak of 1.25 and I think an offset of like 0.25 to make it more difficult on them. I was hoping I could catch students before they made that. Not mistake, because technically the text of the lab manual said to do that, but the picture said otherwise. So, yeah, sorry. But basically, you just need to make sure you write down these values and write down the time of offset. So I basically do that, and you can see here, there's too many steady state points without the offset. Hey, look at that. Now here's the offset, and this is before I removed any steady state points. So we see it's a lot better. We can do better, though. Oh, I think these are actually, these are flipped. But yeah, so we essentially have here our nice graph. Oh, here's something to keep in mind. Oh, that's why. Hang on, sorry. Unhide. Yeah, there's this really weird thing where if you hide this, apparently your graphs do not update correctly. So that's pretty neat. So we have here offset. I need to remove some of this noise, and it looks a little bit better. Cool. Awesome. Something to keep notes. When you take the natural log of a very small number, so for example, a very small number that happens here, they tend to blow up very quickly. So if there's any deviation in the small version, so if we take this out a few more decimal points, so that's 0.0391, we can see here, okay, well, it's going to call me a liar. Pretend this is 5. You will still see like a large enough difference that it shows up in your data. So it might be behooveful to remove more data points where you actually truncate to up here. That's a you decision. Maybe you can include that in your discussion. Whatever works, right? But now we have our slope. Up here, I did the whole 2x2 Linus function, false true, everything's great. Found the slope, found the uncertainty in that slope. You can rearrange it, and you find your tau experimental as well as its standard deviation. Now this is a lower upper. This is one standard deviation. Sometimes you'll see in some academic journals, you'll see 2 standard deviations. That is a statistician thing. They're nerds. Sometimes accessible, sometimes it's unacceptable. You make that deliberation. Here is your theoretical. Again, the tau is just R times C. Something super important. Hope you took a picture of your breadboard. If not, don't worry. I'm going to be posting something on Blackboard regarding your actual capacitor values, depending on which lab station you sat at. If you don't remember which lab station you sat at, I'll make a description of the room. Don't worry. I got you. Hopefully. Maybe. We'll see. Otherwise, I hope your teammates were paying attention. Anyways, on your breadboard, it says you'll have some value, so 470 ohms, and then it'll say plus or minus, I think this is, 0.3%. So to find your absolute uncertainty, take your average value, multiply it by that percentage, they'll give you your absolute uncertainty. Tau is just R times C to find the uncertainty in your theoretical prediction. You guys know it. You guys love it. It's going to be your RSS. Take some derivatives, partial derivatives, multiplications. You all know how to do this. If not, text me, email me. I don't think anyone can text me, so just email me or come to my office hours. That's how you get those values. Fantastic. Now, in your lab report, it says, compare your percent error and discuss differences between theoretical and experimental time constants. Did you verify theory? In this case, my standard deviations actually lie outside the bounds of theory. Why did that happen? Could be a lot of things. Could be maybe the capacitor values were reported wrong, but let's assume they were correct. Could be that the equipment's old. Could be a whole host of things. Maybe here's something interesting to look at. You should look up if electrical components have like an expiration date. If they wear out over time, is something wrong with the breadboard? Could that contribute with something? You guys see noise in our data. What could be is that maybe I should not include these data points right here. I tried tidying it up, but maybe these at the end, maybe that's the noise making it wrong. So maybe my data set should be a lot tighter. So, things to discuss and actually try them. See if that fixes it. See if that goes inside the uncertainty. So, oh, and another thing. I know it says compare using percent error. One thing that you really, really should do is find your ranges of data. I really need to see that because, you might have percent error and you don't really know if 1% is important or not. Because even though it's 1%, maybe I want something with a very tight tolerance. And that 1% actually falls outside the range, right? And that might be a failure in some cases. Something also important is you have to find your 95% time. Make sure you know the start of your transient, so 9181. We are going to go to that cell. And once again, we are going to see where it is 5%, right? So here's my percentage, 9181, go down, and all right. Yeah, we already bled into the falling edge. All right, here we go. 918. Oh, gotta go a little further. 9181. Okay, so it looks like this is the start, right? And now we see where it crosses 5%. Is this part tedious? Yes. Does it suck? Yes. Do you still have to do it? Yes. Sorry. Welcome to being a researcher. All right, so here's something to think about. You have a lot of noise that ends up showing up. So you see here, I kind of chose it at a range where I'm like, all right, it's starting to cross 4, goes back up to 6, goes down to 4, stays under 4. So I tried tightening it up. Essentially, now I have a data range. So I said, okay, here's like my median value. So I'm going to say this is my 95% time. This is the offset time, remember. And then I have an uncertainty or standard deviation of like half that range, right? So if someone ever really cares, if they need to know, this is the reported value. Again, this is in seconds. So that's how you do the RC response. I think that's everything. Oh, make sure for the correct value, the RC circuit was the third capacitor. So make sure you use that value, not the first one. If you guys have any questions, comment it on the YouTube page or YouTube video. Otherwise, email me, and I'll see you guys in the LRC. It's a little more interesting over there.